In this video lesson, we're going to do an introduction to Unit 5, which is forces that are out of equilibrium. Before we can move on, it's important to do a little recap of Newton's first law. If we take a look at Newton's first law, we might remember that Newton's first law stated that objects will keep doing what they are already doing. The more complicated definition was objects in motion will stay in motion, and objects at rest will stay at rest, provided that the force net that's acting on the objects is equal to 0. We gave this term, a definition of term back in Unit 4, and it was called equilibrium. So objects that are in equilibrium are going to be such where the forces that are balanced out. In other words, the net force acting on an object is 0. So let's take a look at a few examples that are in equilibrium. The box on the left, notice, has a force gravity pulling down and a force normal pulling up. Since both of them are equal to 20, we would say the net force is 0 because the y forces cancel each other out, and there are no x forces. In the box on the right, we can see that there are not only y forces, but also x forces. The y forces are going to balance each other out. Force gravity and force normal are both 20, but in opposite directions. And the x forces also cancel each other out. Force friction is 30 newtons, and force applied is 30 newtons. Those cancel each other out as well, so that would also be an object that is in equilibrium. Notice that when we talk about force net of an object, we are analyzing the force net in the y direction and the force net in the x direction separately. So this was a review of Unit 4, where objects are in equilibrium. When we look at Unit 5, we are now going to be dealing with a different situation. So what we see here is what we just saw on the previous screen, where forces that are balanced are in equilibrium, or the force net is equal to 0. However, let's look at a different situation. Let's look at this picture right here. Notice the forces. The force of gravity and the force normal are both 20. So the object is in equilibrium in the y direction. But in the x direction, the force applied is 30 newtons to the right and 10 newtons to the left. In this case, the force net that's acting on the object in the x direction are not balanced. And when forces that are unbalanced come together, they are not in equilibrium. So in other words, the force net would not equal 0, but it would equal some other number. Let's actually think about what it would equal. Well, if you recall from Unit 4, we would always write equations out to demonstrate our vectors of forces in the y and in the x. So let's do the force net in the y first. The sum of the forces in the y direction is equal to force gravity plus force normal, and we know that those are equal to 0 because it's in equilibrium in the y direction. But now let's do the same thing for the x. The sum of the forces in the x direction is equal to force applied plus force friction. Since it's not equal to 0, we're going to leave it just like that. In this case, how would we solve for what the force net actually equals if it's not 0? Well, we plug our numbers in. Now, when we're dealing with objects that are not in equilibrium, it is important to make sure that you establish a positive direction. Typically, the way I will always do these problems is I will make up and to the right both positive. So what that means is this would be a positive 20, this would be a negative 20. And this would be a positive 30, and this would be a negative 10. So when I take my force applied plus my force friction, really what I'm doing is I'm taking my positive 30 newtons plus the negative 10 newtons. And so we get a force net of 20 newtons, and since it's positive, that tells me that it's to the right. So this is an example where an object is not in equilibrium. That leads us to Newton's second law. Newton's second law is not so much words, but it's actually a mathematical equation. And Newton's second law states that force net acting on an object in an x or y direction is equal to the object's mass times the object's acceleration. So in other words, there must be an unbalance of force, or a net force, to cause acceleration. In Unit 4, we were always dealing with a situation where the force net was equal to 0. So that makes sense. Even if you did have a mass, my acceleration would also be 0, because you can't have a 0 force net without having a 0 acceleration. And that's why when you have a 0 acceleration, the object remains at rest, or it remains in constant velocity. In this case now, we're going to see where the object is actually going to accelerate, meaning it's going to speed up or it's going to slow down. And we can use Newton's second law to tell us whether or not the object is speeding up or slowing down. So here's the equation for Newton's second law. Force net equals mass times acceleration. Now, the big idea that I really want you to get from this slide is this. Force and acceleration go hand in hand. Another way of saying that mathematically is that force and acceleration have a direct relationship. What that means is that if the force gets bigger, so does the acceleration. If the force gets smaller, so does the acceleration. Force and acceleration go hand in hand. So if the force net increases on an object, so does its acceleration. And the opposite is true. If the force net decreases on an object, so does its acceleration. That also works for direction as well. Whatever direction the force net is going is the same direction that acceleration is going. So if I were to go back to the previous slide here, notice at the very end I got my answer of 20 newtons, but I also had 20 newtons was the net force going to the right. That also means that acceleration is going to the right as well. One last thing I'd like you to see is this. We've already talked about how force net and acceleration go hand in hand. So if the force gets bigger, so does the acceleration. And if the force gets smaller, so does the acceleration. Once again, that is called a direct relationship. Now, what if you were looking at an object in which case the mass was able to change? So for example, what if I was stating that I want to always make sure a force net of 20 newtons was acting on an object, and I wanted this to remain constant? If the mass got bigger, what would the acceleration have to do? The acceleration would have to get smaller in order to keep that mathematical relationship true. If the mass got smaller, the acceleration would have to get bigger in order to keep the force constant. So we said that force and acceleration have a direct relationship. What would the relationship be between the mass and the acceleration? Well, when one gets bigger and another gets smaller, in math we call that an inverse relationship. So mass and acceleration have an inverse relationship with each other. As one gets bigger, the other gets smaller in order to make sure the force net remains constant. Okay, so let's look at some problems. Let's do some practice right here. I'm going to do the first one for you, and then you're going to have a chance to do some on your own. Let's take a look at the situation that we were just looking at before. You've got your force normal and gravity that are equaled out at 0, but your x forces of friction and applied are not going to be equal. And we've already established on the previous screens that the force net in this example is a positive 20 newtons. Once again, that's the 30 opposing the 10. So 20 newtons to the right. The question is saying what is the acceleration, and then what's the coefficient of friction? Well, to find acceleration, we're going to use our new Newton's law, which is force net equals mass times acceleration. So to do this, my force net is 20 newtons, and what you would need to know is you would need a mass. So we're going to give this block a mass of 5 kilograms. Normally the mass will be given, I just forgot to write it in, so you'll have to have the mass. So if the block's mass is 5 kilograms, we would write that in, and then so we'd be able to figure out that the acceleration is just 20 newtons divided by 5, or in other words, acceleration is 4 meters per second squared. Notice how the acceleration is positive because force net was positive. If force net was negative, acceleration would have been negative as well. Remember, force net and acceleration go together. Now the second question is asking what is the coefficient of friction? This one should be review. Since we're dealing with an object that is accelerating, meaning it's moving, we're going to be dealing with kinetic coefficient of friction. And that's equal to force of friction over force normal. My force of friction I know is 10 newtons. My force normal is 20 newtons. And so my coefficient of friction would be 0.5. Remember, mu is a unitless number. Let's do one more together. All right. In this one, it says a 5 kilogram object is sliding to the right and encountering a friction force that slows it down. The coefficient of friction, mu, between the object and the surface is 0.1. determine the force of gravity, the normal force, the force of friction, the net force, and the acceleration. Sounds like a lot, but it's really not that bad. Before I start with any of the math, the first thing I want to notice is look at the force diagram. You have force gravity down, force normal up, and then you have force friction acting to the left. If you looked at this picture really quickly, you would think that this object is moving to the left, wouldn't you? But it's not. The problem tells me it's sliding to the right. And the reason for that is because, remember, friction opposes motion. If friction is pointing to the left, that must mean the object's moving to the right. So don't think all of a sudden, if you look at the picture, the force diagram, that it's moving to the left. Those are just forces. Remember, forces are going to cause change in motion, not the actual motion itself. Okay, now that we've got that cleared up, let's go ahead and start plugging in some numbers here. I'm told that the object has a mass of 5 kilograms, just like before. So the first thing I can figure out is the force of gravity. 5 kilograms times 10 is going to give me 50 newtons. Now, since this object is in equilibrium in the y direction, meaning there's no acceleration up or down, then I know my normal must be equal to that. And so that's also going to be 50 newtons. All right. Now next, it tells me to calculate my force of friction. Since my force of friction is in a different situation now with acceleration, we can't just look at the x vectors like we would have before. Instead, I'm going to use my equation, force of friction is equal to the mu times the force normal. In this problem, I'm told that the mu is 0.1, and we just solved for my force normal, which is 50 newtons. So my force friction is going to end up equaling 5 newtons. And so I'll write that on my image right here. All right. Then it says, what is the net force? Well, the net force in the y direction is 0 because the normal cancels out with the gravity. But the net force, or sum of the forces in the x direction, just comes from what? Force friction, right? There is no other forces in the x direction. And so my sum of the forces, or net force, is just going to be whatever friction is, which we already know that is 5 newtons. So force net is 5 newtons. And so finally, we can now solve for the acceleration. The acceleration is going to come from Newton's second law. Force net equals mass times acceleration. My force net, is it positive or is it negative? Remember, my positive is always going to be up and to the right. Since my force net comes from force friction, and friction is pointing to the left, then that means when I plug in force net, I'm going to plug in negative 5 newtons. Equals, my mass is 5 kilograms times my acceleration. Divide both sides by 5 kilograms, and I end up getting my acceleration is negative 1 meter per second squared. Once again, notice the acceleration is negative, the force net is negative. Okay, what I'd like you to do is pause the video and try this problem on your own, then hit play to reveal the answers. Okay, first take a few seconds and just analyze the answers in the white box. Force gravity was 40 newtons, force normal was 40 newtons, friction was 50 newtons, force net is 10 newtons, and then the mu, or coefficient of friction, is 0.375. Now, what I'm going to do is real quickly, I'm going to go through those steps just so you can see how I got all those answers. Step 1 is very simple. That's just the force of gravity, which is 4 kilograms times 10. Step 2, since the object is in equilibrium in the y direction and it's on a flat surface, force normal is just going to equal what force gravity is, which is also 40 newtons. Now for number 3 and number 4, where you're calculating frictional force and net force, the problem was presented to you a little bit differently. In this problem, you knew the mass, 4 kilograms, and you knew the acceleration, which was 2.5 meters per second squared. Now this may have tripped some students up, but hopefully you were able to figure out that meters per second is the same thing as meters per second squared. Now, when we take 4 kilograms times 2.5 meters per second squared, that's going to give us our force net, which is the 10 newtons. So force net is 10 newtons right here, which means when you take your force friction and your force applied, and you add them together, you should get 10. That's going to help us figure out what the force friction is right here. So I set it up right here. The sum of the forces in the x direction must equal 10. And what is that a combination of? Well, it's a combination of friction and force applied. Or in other words, friction plus 25, since I know the force applied is 25 from the problem. What plus 25 would give me 10? And the answer is negative 15. Notice that it's negative because it's taking into account the direction. When I report the answer over here on my diagram, I just do the absolute value, since I already know negative is in the left direction. Finally, number 5 wants me to figure out the coefficient of friction. And I know that coefficient of friction is force friction divided by force normal. Notice when I put in the force friction, I only put in the absolute value, since the coefficient of friction is never negative. So I just put in the 15, and I divide that by the force normal, which is 40, to get my coefficient of friction of 0.375. This concludes the video on the introduction to Unit 5 and Newton's second law.